Hey there, everyone. So lately we have been talking a lot about genetics and Mendel's experiments, and one of the most useful and important applications of a lot of what we learn in genetics is the pedigree analysis. So, reading pedigrees is usually not too difficult, but what can sometimes be a little bit challenging is using a pedigree chart to assess probability and risk associated with passing on a harmful trait. Now, not every trait is necessarily going to be harmful when you consider a pedigree analysis, but I did want to record this video just to kind of give us some practice and some exposure with calculating probability using pedigrees. So, without any further ado, let's go ahead and get started. So this pedigree that you're looking at right here spans 5 generations. You can see we have generation 1 up here, generation 2 down here, 3, 4, and 5. So specifically what we're looking at here is albinism. So albinoism is basically a autosomal recessive trait. I'm not going to call it a disorder, but it is a autosomal recessive trait, meaning that the only way that you are going to be affected and have albinism is to have a genotype of little c, to have both recessive alleles. So as you read the chart, anytime you see an individual who's circle or square, a circle is a female, a square is a male, anytime you see the shape completely shaded in, you can go ahead and assume that that person is an albino and has a genotype of little c. Now, for all the other shapes, which are the other squares and the other circles that are not shaded in, that must mean they are either homozygous dominant, capital C, or they are a heterozygote, capital C. So basically, as we're going to kind of fill in all as much information as we possibly can here, basically what you're going to be told for the sake of this activity is that unless you have evidence to the contrary, you can assume that any men or women that marry into this particular family, any men or women who marry into the albino family, you can go ahead and assume that they are homozygous dominant and they are not carrying the albino trait. Okay, so the first thing we want to do is we want to fill in as many knowns as possible. Now, as we said, any of the shapes, any of the individuals that are not shaded in, they can technically either be capital C or capital C. But there are some important inferences that we can make. First, we can infer that this man right here that marries this albino woman, we can infer that he must be a heterozygote, because if you look at their 4 children, they produce one child who is an albino. If this man right here, if this man were homozygous dominant, then it would not be possible for them to produce an albino child. The only way they could produce an albino child is if he is heterozygous. Next, if we start looking at the second generation, we can go ahead and say that both of these individuals must be heterozygotes, because you can obviously see that they do produce one child who is an albino. Since these 2 individuals are not shaded in, we can go ahead and eliminate the possibility that they are homozygous recessive, because they do not outwardly express the albino trait. That would be very obvious to see. But since they have one albino child, they must both be heterozygotes. Next, this individual right here, we can go ahead and say is capital C, so a homozygous dominant, but for 2 reasons. Number 1, we can see that he married an albino woman. They did not have any albino children, but that in and of itself is actually not enough to definitively say that this man is homozygous dominant. Just because they had 4 unaffected children doesn't necessarily mean that they can't produce an albino child. Maybe they just got lucky. Maybe they just beat the odds. If they had a 1 in 4 chance of having an albino child, maybe they just got lucky. Or if they had a 1 in 2 chance, maybe they just got lucky. The reason why we're definitively calling this man capital C is because of that statement we made on the previous slide. Unless you have evidence to the contrary, that evidence would be if they had an albino child. If they did have an albino child, we would call him a heterozygote, but since we do not have that evidence, we are instructed to assume he is homozygous dominant. So this man here and this woman here must be heterozygous, again for the same reason as before, because we can clearly see that of their 3 children, one of them was an albino, so nothing too terribly interesting there. So this man right here must be heterozygous, so you can see his entire closely knit family here, his immediate family here, they're all unaffected, but we know he at least has to be a carrier for the trait because of who his parents were. So his father is a heterozygote and his mother is albino. This woman right here, for the same reason that we said before, we can go ahead and assume she is homozygous dominant, but we're not going to go to the trouble of filling that in. Okay, if we start skipping down to the 3rd generation, this man right here, individual number 5, we can go ahead and say for sure he is heterozygous because we know that that has to be the result of the mating between his father and his mother, capital C, and little c. The only possible progeny would be heterozygotes, so the same thing would go for his sister and his other brother as well. Individual number 8 right here, again, should also be heterozygous because these are all the 4 children of this mating right here, and they all must be heterozygous. And up until this point, this is about all we can say for sure that we know. Any of the individuals that you do not see any information filled in for, it is not definitive. It could be this or it could be that, and that's going to be part of what we try to figure out next. So a couple of general statements we can go ahead and make. The parents in the 1st generation way up here, they are capital C times little c. As we said, they can only have children that are either heterozygotes or albinos. That's why you can see here one of them absolutely is albino. And then the ones that we can see with our eyes are not albino, they must be heterozygotes. And then as we're going to see, if a heterozygote marries outside the family and gives rise to an albino child, then the other partner must be heterozygous because that is the only way 2 unaffected individuals could have an albino child is if both parents are heterozygous. Okay, so what we are going to do now, and we'll do several examples of this for calculating probability, we are going to determine the specific probability that given matings will produce an albino child. Now, for the sake of this activity, you can see that this is an entire family, so this is an entire extended family. So for the sake of this activity, we are going to suggest some consanguineous marriages, meaning that marriages between closely related individuals. So obviously that's pretty usually frowned upon, but for the sake of this activity, let's just go ahead and assume that it's allowable. So let's just kind of cut ourselves a break on that just to make sure this activity works. So what we're going to do first is we are going to have individual number 4, who we saw before is an albino, is going to mate with individual number 7, who we saw before is a heterozygote. So we can see this arranged marriage right here. So this is between this woman right here who is albino and this man right here who is heterozygous. So we saw before that an albino child would not be possible if one of the parents is homozygous dominant, but since man number 7 here is not homozygous dominant, we do have at least some probability that individual 4 and individual 7 could have an albino child. So let's figure that out. So we know individual number 4 is homozygous recessive, so she has a 100% chance of passing on her albino allele, okay? But individual number 7, since he is heterozygous, he only has a 50% chance of passing on the recessive allele. So when we're calculating the probability that they're going to have an albino child, we have to specifically consider the probability of the child receiving a recessive allele from the father and a recessive allele from the mother. So since those are non-mutually exclusive events, we use the product rule. We take the separate probabilities of getting this little c allele from mom and the little c allele from dad, and we multiply those 2 probabilities together. So what we would do here is that since mom has a 100% chance of passing on her recessive allele and dad has a 50% chance of passing on his recessive allele, you multiply those 2 probabilities together, and you can see this also in a Punnett square. two of the four possibilities would produce an albino child, so there is a 50% chance that 4 and 7 producing a child, that child would be albino. Okay, so that was a pretty easy one, so let's move on to one that's a little bit more challenging. This time we are going to mate individual number 5 with individual number 1. So we can see that individual number 5 is a heterozygote, so just like we saw before, he has a 50% chance of passing on the albino allele, the little c allele, which means that if he mates with another heterozygote, then that probability would technically be 25%. So, but that's assuming that individual number 1 is a heterozygote. But we don't know that for sure. Individual number 1 could be heterozygous, but she could also be homozygous dominant. And if she's homozygous dominant, then there is no chance that they're going to have an albino child. So this is a separate probability that we need to consider. We need to consider the probability that individual number 1 is a heterozygote. So in order to do that, we need to look at her parents. Her parents are both heterozygotes, so we need to put together a Punnett square to come up with all the different ways that individual number 1 could be a heterozygote. Now, if you'll see here, if we put together a Punnett square for her parents, then we can see that of the 4 possibilities, 2 of the 4 would result in her being heterozygous. 1 of the 4 would result in her being albino herself, and then the other possibility of the 4 would be her being homozygous dominant. But if you come back here, it says that technically she has a 50% chance of being a heterozygote just on the basis of that Punnett square, but we know she is not an albino because we can look at her with her eyes and see that she is not albino. We can see that she's got some pigmentation in her skin and in her hair. So we can actually eliminate that 4th possibility, meaning that now we're only considering 3 possibilities. 1 of the 3 she's homozygous dominant, and the other 2 she is a heterozygote. So instead of calling this a 2 in 4 possibility that she's heterozygous, it's instead a 2 in 3 possibility because we know she is not an albino. So in order to calculate the probability of her being a heterozygote, we just saw that that's 2 out of 3. And then we can put together a Punnett square on the basis of her being a heterozygote and then her husband being a heterozygote, which we already know. And on that basis, we see that they would have a 1 in 4 chance of being a heterozygote. So we would multiply those 2 probabilities together. The 1 in 4 probability that if they're both heterozygotes, that they would have an albino child, multiplied by the 2 in 3 chance that she was a heterozygote to begin with. So what that would give us, as we simplify this fraction down, is a 1 in 6 chance that the child will be albino. Okay, so next we are going to mate together individual number 6 and individual number 13. So we see something very similar here. We know that individual number 6 is a heterozygote, so we're going to apply the exact same logic we did before. We know she's heterozygous, we know she has a 50% chance of passing on the albino allele, and now we have to calculate the probability that this man right here, man number 13, is a heterozygote himself. So we don't know his genotype, his father's a heterozygote, and his mother we can assume is homozygous dominant. So really, individual number 13 has a 50% chance of being heterozygous himself. Now, this is a little different than what we saw before, because what we saw before, when we looked at individual number 5's, or which one was it? It was individual number 5's, number 1's parents. Individual number 1's parents were both heterozygotes, so that was we had to upgrade that possibility to 2/3. In this case, we know that one of his parents is homozygous dominant, so we don't have to do that 2/3 malarkey. So here we can actually see that individual number 13 has a 50% chance of being heterozygous. So this one's a little bit easier. We calculate the 1 in 4 probability that 6 and 13 would have an albino child if they're both heterozygotes. And then for person number 13, there is a 50% chance that he is heterozygous to begin with. So for this mating, there would actually be a 1 in 8 probability of them producing an albino child. Next, we'll do 10 and 14. So this is a very interesting one because we actually do not know for sure the genotype of either man number 10 or woman number 14. So all we really know about them is that they are not albino. So they are either going to be homozygous dominant or heterozygous. So the only way that there's going to be any possibility that 10 and 14 will produce an albino child is if they're both heterozygous. So what we're going to calculate here is the probability that each one is a heterozygote. So we're actually going to have 3 different probabilities that we're going to have to multiply together. The probability that 10 is a heterozygote times the probability that 14 is a heterozygote times the probability that if they are heterozygotes that they would actually have an albino child. So for individual number 10, we see something very similar here, what we saw before with individual number 1. His parents are both heterozygotes, so he is actually going to have a 2 in 3 chance of being heterozygous himself. We know he's not an albino, so it's 2 in 3 instead of 2 in 4. And then individual 14, just like we saw before, has a 50% chance of being heterozygous because her mother is actually homozygous dominant. So the probability here is going to be, we saw for individual number 10, he has a 2 in 3 chance of being heterozygous. Individual number 14 has a 2 in 4 chance of being heterozygous. And then together they have a 1 in 4 chance of producing an albino child if they're both heterozygotes. So this would be 2 in 3 times 1 over 2 times 1 over 4. So altogether, this would produce a 1 in 12 chance that they would produce an albino child. All right, next we will move on to 3 and 17. So another challenging one in the sense that we don't know their genotypes right off the bat. So we know for sure we're going to have to calculate the probability that each one is heterozygous. So this is actually fairly simple for individual number 3. As we saw before for individual number 1, his parents are both heterozygous, so he has a 2 in 3 chance of being heterozygous himself. 17 is a lot more challenging because we do not know the genotype of 17's mother. We know the genotype of 17's father, but not of 17's mother. So in order to help us determine the genotype of 17's mother, we are going to need to calculate the probability separately that 17's mother is heterozygous too. So there are actually going to be 4 probabilities that we have to calculate here and multiply together. We have to calculate the probability that 3 is a heterozygote, that 9 is a heterozygote, that 17 is a heterozygote, and then if 17 and 3 are heterozygotes, the 1 in 4 chance that they would have an albino child. So as it says here for 17, we actually need to go back 2 generations. We see that her mother, we don't know her genotype, so to figure that out, we need to look at 9's parents. 9's parents are both heterozygotes, so technically 9 has a 2 in 3 chance of being heterozygous herself. So the probabilities that we're going to put together here is 2/3 for individual number 3, 2/3 for individual number 9, 1/2 for individual number 17, and then 1/4 for the 3 times 17 mating. So for the grandparents of person number 17, you can see the 2 in 3 probability there. The parents of person number 3, a 2 in 3 chance of him being heterozygous. The parents of person number 17, we saw that her mother had a 2 in 3 chance of being heterozygous. So this is based on the on the assumption that her mother is heterozygous. And then finally, the mating that we see here between 3 and 17, if they are both heterozygous, they have a 1 in 4 chance of producing a albino person or an albino child. So 2/3 times 2/3 times 1/2 times 1/4 gives us, as we simplify this fraction, a 1 in 18 chance that they would produce an albino child. All right, next we will do 3 times 15. I think this one's going to be a little bit more simple. So 3 and 15, we again see that we do not know either of their genotypes. We've seen before for the children of these parents up here, number 3 has a 2 in 3 chance of being heterozygous. Now for 15, we can clearly see that 15 has a heterozygous father and a homozygous dominant mother. So there is a 50% chance of him being heterozygous, or her being heterozygous herself. So this one's a lot easier. We see the 2 and 3 chance of person number 3 being heterozygous, the 1 and 2 chance of person 15 being heterozygous, and then the 1 and 4 chance of these two together making an albino child. So we get another 1 in 12 possibility. Okay, and I think this is the last one. There may be one more after this, but I actually think this is the last one, so apologies if I'm wrong about that. 16 times 17. So this is at the very bottom of the pedigree chart. So we can see here, once again, we do not know either of their genotypes, but we can see that 16 has a heterozygous mother and a homozygous dominant father. So he, of course, has a 50% chance of being heterozygous himself. 17, we can see that she has a homozygous dominant father, so the only way that she could pass on the recessive allele herself is if her mother is heterozygous. So again, we have to calculate the probability that her mother is heterozygous. So you'll recall that that was a 2 and 3 possibility, so that's just another thing that we have to tack on there. So we can see here that we have to calculate for individual number 17, we have to calculate the 2 and 3 probability that her grandparents would produce a her heterozygous mother. Then for her heterozygous mother, the 1 and 2 possibility that they would produce a heterozygous daughter. And then for the parents of 16 here, that is the 50% chance, and then finally the 1 in 4 chance that you see right here. So 1/2 times 1/3 times 1/4 times 1 in 24. So if you look at 17 here, you can see it's a little bit different. So 17 has only a 1 in 3 chance of being a het because her mother had a 2 in 3 chance of being a het, and 17 has a 50% chance. So we kind of combine some of those probabilities in there. So technically what it should be is 1/2 times 2/3 times 1/2 times 1/4. But the reason why it's 1/3 there is because we actually combined 1/2 and 2/3 together. So there actually should be 4 probabilities we're multiplying together here. So the fact that it's only 3 of them, 1/2, 1/3, and 1/4, the 1/3 is because we multiplied together 1/2 and 2/3 to get the 1/3. So in this case, we have a 1 in 24 chance overall. All right, so that's going to do it for this little activity. I certainly hope you found it useful. So next time we will delve a little bit further into genetics. I'm not exactly sure when you're going to be watching this video compared to when you're watching all the other genetics videos. But again, I hope you found it helpful, and I will see you next time.